Alrighty, today we're going to be talking about protons, neutrons, and electrons. So as we've discussed today, we ended up with the Bohr model for the atom at the end of the atomic theory. And the Bohr model of the atom has the atom made up of protons, neutrons, and electrons. The electrons are orbiting the protons and neutrons, which are in the nucleus, and the electrons are orbiting them in very specific and discrete orbitals or shells. So let's ask ourselves a question. What makes up an atom? And the atom is made up of a nucleus with protons and neutrons inside of it, which are surrounded by orbiting electrons. Some specifics on each particle type. A proton is typically symbolized by a P with a plus sign, or a hydrogen, because a hydrogen is merely just one proton. It has a charge of 1 plus and a mass of 1.673 times 10 to the negative 24 grams. A neutron, found with the symbol of N with 1 0 next to it, has a charge of 0, it is neutrally charged, and a mass of 1.675 times 10 to the negative 24 grams. So as you can see, the mass of a proton and neutron are almost identical, with a neutron just having slightly more mass than a proton, but hardly any, but not that much of a difference. Electrons have a symbol E minus, and they have a negative charge and a mass of 9.109 times 10 to the negative 28. They are much, much smaller in mass and size than both protons and neutrons. With all elements made up of protons, neutrons, and electrons, the distinguishing part is that different elements have different numbers of each of those particles, protons, neutrons, and electrons. So atomic number. The atomic number is what distinguishes elements from each other, and it's the number of protons. Each element has a specific number of protons, and this value is described as the atomic number, or Z. So for example, fluorine here has, and this is what a tile on the periodic table looks like, fluorine, the atomic number is 9, so fluorine has 9 protons in its nucleus. Another example would be that oxygen has 8 protons, and so the atomic number of oxygen is 8. Atomic mass or atomic weight. Now, either of these titles is completely appropriate. It's just kind of a different vocabulary style, whether you call it atomic mass or atomic weight, and different books utilize different vocabulary. So I'm trying to introduce you to both of them to remember that they are the same. The atomic mass of an element is a weighted average of the mass of the atoms in a naturally occurring sample of the atoms. This means that the atomic mass of carbon is the weighted average of all the different atoms of carbon, what each of those individual atom weighs. It's a weighted average. So the mass of an atom is primarily made up from the protons and the neutrons, as electrons are 1,000th the size of a proton. So the atomic mass depends on the number of protons and neutrons within that atom. So for example, fluorine here again has 9 protons, and on the periodic table you can also see what the atomic mass or the atomic weight is, and it's located at the bottom. Its atomic mass is 18.9984032. So the atomic mass or weight is usually the number associated with the atom that is a decimal. So it has decimal places. Everything else is going to be usually found as integer values or whole number values. But the atomic mass, since it's a weighted average, oftentimes is found with decimals, unless you're getting into the large or radioactive elements, in which case a lot of the times these are too short-lived for us to accurately determine the atomic mass to weigh it, and so they have whole numbers because it's not really a weighted average so much as just an assumed value. So the mass number, this is the number of protons and neutrons in an atom, and it is called the mass number. Now, different atoms of the same element can have different numbers of neutrons, so the mass number is not a value that you're going to find on the periodic table. So there is no value here for fluorine specifically for the mass number of fluorine. Since the number of neutrons is specific to the atom itself and not specific to the element, It's used as an identifier in naming a substance. I'm going to repeat that again because of the bell. It is used as an identifier in naming a substance. So for example, you can have uranium-235 or uranium-238. And the difference there is that uranium-238 has 3 more neutrons than uranium-235. Now we're going to get more into what happens when you add different numbers of neutrons to elements, but the important thing to remember is that each element can have multiple numbers of neutrons, and these are called isotopes, but we're going to get into those later. So the question is, how many neutrons do you have? The number of neutrons of a given element can be determined if you know the following: the atomic number and the atomic mass. And that's where that A and Z came into, A and Z came into effect, is that A is the atomic number, so the mass number, so the number of protons and neutrons. A is the mass number, the number of protons and neutrons, and Z is your atomic number, the number of protons. E here standing in for whatever element you're talking about. If the atomic number found, which is found on the periodic table, is known and the mass number is given, then by subtracting the atomic number from the mass number, the number of neutrons can be found. So that was a lot of words, so let's look at an example. Gold has a mass number, which we would be given, I would say gold 197, has a mass number of 197. On the periodic table, we can find that its atomic number is 79. So with a mass number of 197 and an atomic number of 79, you can determine the number of neutrons by subtracting 79 from 197. If you take 79 from 197, you get 118. So there are 118 neutrons for 79 protons in gold. And you'll notice that the number of neutrons is usually larger than the number of protons, especially when you get into much larger atoms. And this is because with so many protons, which are positively charged, the more you get, the more strong the repulsive force is between those positively charged particles. And so the more neutrons you have to have in there to counterbalance that repulsive force. And this is kind of what we were talking about with Maria Geopère-Mare, is that she found that magic number. And if you noticed, it went from 6 to 8 to 20 to 28, then to like 50 and 126. And it started escalating. The change in the number got so much larger each time because you're adding more repulsive force in there. So the question is then, how do you find out how many protons? And like I said, the number of protons is equal to the atomic number, which can be found on the periodic table. So all you have to do is look at the periodic table. So here I have 3 tiles of different elements that you would find on the periodic table. I have krypton, tungsten, and scandium. And so if you look, I've circled the number, which is the atomic number, which is the number of protons. And so krypton would have 36 protons, tungsten would have 74 protons, and scandium has 21 protons. So to find the atomic number or the number of protons, all you have to do is look at the periodic table, and it's written right there. And then the number of neutrons would be found by the given mass number, which would have to be given to you. You cannot just determine it, and then subtraction to find the number of neutrons. The next question is, how many electrons? And if the atom you're describing is a neutrally charged atom, then the number of positively charged protons must equal the number of negatively charged electrons. In order for that atom to be neutrally charged, meaning it has 0 charge, the number of pluses has to equal the number of minuses. That way they balance each other out. So for example, if I was looking at phosphorus and strontium, phosphorus has 15 protons and strontium has 38 protons. So phosphorus would therefore have to have 15 electrons, and strontium would have to have 38 electrons to balance out those 15 protons and 38 protons. So when we get into losing and gaining electrons, we'll talk more about how that affects the charge and what then happens, how you do the math to figure out how many electrons. But for a basic just background knowledge of determining the number of electrons, you just look to see how many protons are there as well. Alrighty, that's it for today. You're going to come in tomorrow and we're going to work on a worksheet where we determine the number of protons, neutrons, and electrons based on different given information, and sometimes even figuring out, based on the number of protons and neutrons and electrons, what element I'm actually describing. Have a good night, you guys.